Hello everybody, so I'm just going to show you real quickly the difference between average velocity speed and instantaneous velocity and speed and how to calculate it. So let's just say that we're going from Bismarck to Fark. So we know that the distance is, about 200 miles or 190, but we're just going to say for this purpose that the total distance is 300 kilometers or 300,000 meters. And we're using meters because our average or our velocities and stuff are usually done in meters per second. So let's just say that it took you 2.5 hours to get there, which is going to be 3,600 seconds, because that's how many is in an hour, times 2.5, because we are going to get it meters to second. So that's 9,000 seconds. Okay. Now that's how long it took to get there. And say that this is our distance. Okay. So, like you already know from the video before, your distance is going to be your total amount of travel. So if it's a distance, then it's going to be a speed. Okay. So our speed is distance per time. And our speed then in this case is going to be 300,000 meters divided by 9,000 seconds. Okay. Okay, so it's 300,000 meters divided by 9,000 seconds. That's going to equal 33.33 meters per second. Now that's your distance divided by your time. So that includes, like I said, all the curves and every inch that you travel is counted up in this. Okay. Now the only thing is, we also talked about velocity, and so distance per time is usually what we use. But I'm going to show you the difference between velocity and x over t is a typical formula. Okay. So the velocity in this case is going to be different than your speed. Okay, so this x up here, that could be for anything. But that's usually commonly used for displacement. So the difference here is going to be if this is straight the whole entire way. Now that's not that straight either, but it's going to be less than distance, right? So the displacement, let's just say, is 280,000 meters. And your time then is still 9,000 seconds. This is kind of a funny pen. Let's see if I can change it for you. Okay, so that's getting kind of weird there with the pens. Now, so your velocity then is going to be a different number. So that's going to be 31.11 meters per second. Now, velocity doesn't have just size, so it doesn't just have this number. It also has direction. Now, we can assume this is positive because there's no other direction here. If it's velocity, then you're going to have positive and negative. But in this case, we could say that it's actually east. And when we get, a little further into this course, we're going to have to be really careful with our directions. Like east is only going to mean directly east. So usually there'd be a little bit more to it, like angle measurements and things, and we'll get into that. But here's your 31.1 meters per second east versus your 33.3 meters per second for your speed. Now, there's another thing that I wanted to tell you, and that is that these velocities and speeds here are averages. Okay, in this case, it's an average. And why is it an average? Well, if you think of yourself driving, and I'm sure all of you are driving right now, there's this little thing on the ground. It's connected to a little thing in your car, and you got your foot here, right? And what do? You put your foot on the gas pedal, and you're pushing in, relieving to try to maintain that exact same speed the whole time. Even if you have cruise control doing this stuff for you, you can still see your speedometer. Speedometer is bouncing, from 70 to 71 or 72 back and forth. And so you know that this speed is constantly changing because you have to constantly change the pressure you put on your gas pedal because of air, bumps, hills, and things like that. So that's why these two things are definitely average speed and average velocity. And so what I mean by that is, if you have a velocity time graph, when you're going to Fargo, you're going to start out and you're going to accelerate, and then you're going to maintain an almost average velocity, but you're going back and forth and back and forth. And then maybe you might stop to go to the bathroom. And then you get going again. And then before you know it, you're finally at Fargo. Okay, so this might be your actual look of your graph, of your velocity time graph. So what do you do here? What we did is we took this average velocity. So if you take that velocity time graph, the same one there, and turn it into a distance, or actually this would be a displacement time graph, right? But if you had a displacement time graph, then you would see that you're, changing quickly, and then you maintain, maybe get a little faster, and then you stop, and then you quickly change, and then you kind of go like that. So this would be your distance time graph. I said displacement, but there's a reason. Now this could be displacement too. The only thing is we knew that we curved around. We went south. So we were going, from Bismarck to Fargo. We went like this, and then we went down. So we're going in two different directions. We're going this way and that way, and then we're going this way and that way. And if you look on a graph here, you can only have two directions on each graph. You could never have four. So knowing what we know about this, we would probably say that this is mostly considered a distance time graph because you can only have two directions. Now, the reason I drew this is because I wanted to show you what we did here for what we did for our average velocity or average distance, same thing. We took that point, and oh, that wasn't very good, but it should be like a straight line right there. And then we took our average. So just in case you don't get what I said because of my drawing there, imagine that we have a graph that's like this, make it more distinct. Then we take and say, well, from here to here is our average distance or speed. Now, if you keep in mind what's going on here, this is meters over seconds. So the slope of this line is equal to rise over run. In this case, it's meters over seconds. So see your y's over your x's in slope form. This is meters per second. So keep in mind, from now on, you're going to have to know that every time you have a slope of a graph, there's a meaning to it. And if you put the labels in order of the slope, then you know the meaning. So in this case, it's meters per second, which could be distance per time or displacement per time. Okay, so to find an instantaneous velocity, it's a little bit different because, you know, if your velocity looks like this, you can find the average of that whole entire time by going from here down to here. But what if you want to know something different? What if you want to know what the velocity is at this point right here? Or what if you want to know what it is at this point right here? So that would be what we call an instantaneous velocity because it's happening at these instants in time. And so what do? Well, you draw a tangent line. So let's see how well I can do this. Oops, it doesn't look very good to start. Okay, so tangent is supposed to touch the graph or a curve at one point and only one point, right? That's a little better. Those would be tangent lines. And those tangent lines at these points in time, so the tangent to the curve at those points in time is what would be considered an instantaneous velocity. So what you'd have to do, you know, it could be velocity, or this could actually be speed too. I'll tell you the difference here in a sec. But what you'd have to do then to figure out what the instantaneous velocity is you'd have to take a point there, you know, a point here, and then take the rise over the run of this slope line, and then that's how you get your instantaneous velocity at these points in time. Just like this one here too. So you can see these slopes are different, right? This one's different than that one. And you know, the question is, what does that mean? What does the difference mean? So these could be instantaneous velocities or instantaneous speeds because you could have either in this type of distance time or displacement time graph. Now, just to kind of refresh your memory, if you have, you know, a slope here, okay, so I'll put a little mark there so you know what that one is. And if you have a slope here, you know, that red one, there's a slope, and you know, you have another slope here. The question is, what's the difference between these two slopes? Okay, so if this is a distance time graph or displacement time graph, you gotta ask yourself, what's the difference? Well, this first one here is gonna be the slowest because it has the smallest slope. This one here will be medium, and this one will be the fastest, okay? And so that's all there is to it, is that the slope indicates the rate. And so if you look here at this, let's just look at this point in time right here. So this made that much distance. Whatever's on this slope has made that much distance. Whatever's on that slope has made that much distance. So you can tell that there's, you know, much more distance per time, and therefore it's going to be faster. Yeah, so you should keep in mind that the steepness of the slope will indicate how fast it is. And why I say steepness instead of you know, more or less positive is because you know, I showed that I have that slope, right? But you know, what happens if I have a no slope? So let's say I have a distance time graph and I have no slope. Well, that means that I'm not going anywhere. You know, that's why I'm staying at the same distance or displacement, okay? What if I have a negative slope? Okay, so if I have a negative slope, that means I'm going in the negative direction. So this is where this graph can only be a displacement time graph. And if it's a displacement time graph, it can only be velocity. So you look at these two graphs. Okay, so this is back to the whole idea of steepness. Now, oops, this one is steeper than this one. And if you look at it, you will see that, in the same amount of time, there's a difference in displacement here that's bigger than a difference in displacement there. So you're moving across meters faster with a steeper slope. Now it's negative, but it's going to be a larger negative slope than this one right here. And I don't know if you say larger mathematically or not, but the number's bigger on a steeper slope, even if it's negative. So this, the way this is, could be speed or velocity. This could only be velocity because there's only negative when we have our vector quantities. Okay, so velocity is your vector, which can be, it can be positive or negative. Speed can only be positive. And those are called scalar quantities. Velocity then is a vector quantity, and speed is also a scalar quantity. So hopefully that clears some things up here for you.